Thank you for being here. Last session before almost the closing. I'm here to talk to you about how we move a Java product to Kubernetes and the lessons we learned, the good things, the bad things. I'm not here to sell you anything, so I hope that if you're planning to do something like this is somehow useful for you. But before we start, some questions. Who is using Java? Okay. Who is using Java on containers? Okay, some people. Who is using Kubernetes? And Java on Kubernetes? Not that many people. Okay. So I'm Carlos Sanchez. I'm a principal scientist on Adobe Experience Manager cloud service. I have a background on open source. I started the Jenkins Kubernetes plugin, and I have contributed to a bunch of open source projects, Jenkins, Maven, Puppet, and a few other things. And some short introduction about Adobe Experience Manager. It's a content management system with digital assets, digital enrollment forms. And it's not widely known, but it's used for a lot of big enterprises out there. On the technical side, it's a distributed Java OSGI application that uses a lot of open source components from the Apache Software Foundation and other places. And one interesting point is that it allows developers to write code for AM. So this is going to be interesting later. How did we move this to Kubernetes? We're currently running on Azure. We have more than 35 clusters. And because it's a content management system, customers want to have the content be delivered as close as possible to their customers. So we have a lot of different regions. And these clusters, at Adobe, we have a team that manages them from us, and we take over from the Kubernetes cluster up the stack, and then there's the application level and so on. So there's multiple layers. What we call today more of a platform team or developer experience team. Interesting points, because we run customer code. So we get code from the customer that we incorporate in this Java application, and this is run in our clusters. We have to ensure that multi-tenancy, we limit a bunch of cluster permissions, so we cannot do a lot of things that we would like to do if this were not a multi-tenant application. Things like traffic getting out of the cluster must be encrypted, and all the typical security considerations that we have to do. On AM, we have this concept called AM environments, and customers can have multiple ones, and they can self-serve. So we have now, I think, 17,000 environments, and customers can create new ones whenever they want. And this translates to Kubernetes namespaces. We have multiple Kubernetes namespaces for each customer. And each environment, each of these AM environments, we call it, I like to call it a micro monolith, in the sense that it's a monolith that we replicate, and we give each customer one copy. So it's a slightly different variations of the same Java application. On Kubernetes, you can use namespaces to provide the scope. It allows you to do network isolation, quotas, permissions. So that's why we chose the namespace level as one of the isolation layers for the Java application. We have multiple teams building services, and we try to follow this you build it, you run it philosophy. So different teams can choose what's for the new services that they're creating. They can choose whether they want to do it in Java, in Golang, Node, whatever. And we use a lot the Kubernetes operator patterns, which means more of an asynchronous nature. You create objects in Kubernetes, then an operator comes and picks up those changes and acts based on that. So it's a bit of event-based and asynchronous architecture. We also use APIs for REST calls and more synchronous nature. On the environments, we use init containers and many sidecars to do a division of concern. So on Kubernetes, for those that are not familiar with, when you run a container, you run it in a pod, and you can have multiple containers per pod. One thing you can do is also have init containers. So you have init containers that start at the beginning, they finish, and then the next init container, and so on. So you have some initialization phase. And then you have the main containers, which is typically your main application, and sidecars are other containers that run with that main container. And all of them share the network namespace, they share different resources, you can share disk across them, and so on. So it's a very popular pattern. And it allows you to do division of concerns easily for things that you don't want to do a separate service, but you want to run next to your application. So for the sidecars, we have a list of them, like service warm-up, storage initialization. We have HTTPD in front of the Java application. This comes from the non-Kubernetes days that already existed. How to support metrics, how to send loss, how to do thread dump collection, how to auto-update these containers. Instead of putting them in the main application, in the main container, we have sidecars so they can move at different speeds, or typically higher speeds than if they were in the big application. One of the sidecars is, for instance, the service warm-up. So this, when you start the container, the service warm-up hits the most popular URLs. It gets the most popular URLs for that environment, hits them to make sure that the cache is populated before saying this pod can take traffic. So it does this lazy caching, and it allows us to have the pods ready for when the traffic is about to start. Otherwise, what typically happens when the caching is not right, and it happened before, you start a pod, the process comes up, Java comes up, is serving traffic, that pod becomes part of the load balancer, and then it starts getting requests, is not able to cope with the request because caching is not warm, the cache is not warm, and that causes a cascading effect because that pod it stops being ready, and then you need to start more pods and so on. So this is an important thing that we had to do. For exporting metrics like this size, this space, network reachability, we also put it in a separate container, so we can move at a faster speed when we want to just make small changes for these sort of features. Fluent bit to send logs. So you can share, as I mentioned, you can share a file system between all the containers in a pod. What happens here is all the applications write to this share file system, and then one of the containers reads that file system and sends the logs to the outside. And you don't need to you don't need to code the logging in each of the containers in the pod. And you can also configure it independently of the application. You don't need to change the application to change how the logs are shipped. Thread dump collection, something similar. We can generate thread dumps from the JVM. Those are stored in a shared location, and this other container, if they're sending new files, ships them to a shared location. Something a bit more complicated that we did was proxying with Envoy. Envoy is a proxy that is very popular on the Kubernetes world. And we use it for traffic tunneling and routing. It allows us to have different IPs per pod or per customer, and allows us to have VPN connectivity per customer. So every time a customer wants to have a dedicated IP, when they go to the internet, basically, by default, Kubernetes, you're going to get dynamic IPs from the pool. What we do here is we configure the JVM to send traffic to Envoy that is running next to it in the same pod. Envoy then sends that traffic through a specific IP that is not shared with other customers. And we do MTLS and certificates to ensure that this all is trusted, but allows us to have both an IP that a customer does not share with other customers, because this is a multi-tenant service, and also connect to their VPN if they need to do some. They need to connect to some backend that they have on their VPN. Envoy has a lot of features. It's a very full-fledged proxy, allows you to do rate limiting, circuit breaking, retries. It's very, very, very powerful. Another container that we created, and this came from the Log4j issue that probably everybody's aware of, and allows us to, on a startup, change things on the application. So we can do, let's say we want to replace a Log4j version with another version for things that are older without having to redeploy everything. We can go and do that. On the init container, we can go and look at the file system and say, okay, it's using the old one, use this one. This is useful when you want to change files that are more infrastructure-like, like JVM agents, for instance. Instead of repacking, rebuilding your application, your Docker image, and think that we have hundreds of customers and we would need to do this for each of them because each of them has different code, we can do it more on the infrastructure layer, saying every time the container starts, do this before. And this allows us to patch the whole cluster fleet from one common shared place. One tricky thing for Java on Kubernetes is the scaling and the resource on how to optimize resources. On our case, we have more than 17,000 environments, and this is like this micro monolith that I mentioned before. And we have multiple services that multiple teams that are building services. So we need some ways to scale and to optimize resources that don't involve going to each team and saying, okay, you need to do this, you need to do that, you need to do this other thing. So we look at the whole thing and how can we dynamically improve things without having to go to each of them. On Kubernetes, for those of you that are not familiar with, you have resource requests and limits. So from a high-level point of view, request is how many resources you have guaranteed. So you are actually guaranteed that in that node you're going to get those resources. And limits is how many resources you can consume. And you can consume more resources than the ones you request. And this is applied to CPU, memory, and ephemeral storage. What happens when you go over your CPU limits? You can end with CPU throttling. When you go over your memory limit, your process is killed. The kernel is going to go and kill your process because you went over your limit. On CPU, no. CPU, unless you go over the limit, it just throttles you, so you don't pass the limit. On the ephemeral storage, if you use more storage than you request or that you set as limit, it's enforced and your pod is going to be evicted. Evicted means your pod is going to be deleted from that node and Kubernetes is going to schedule it in a different node. So imagine you are using a lot of disk. It gets to a point that you go over the limit. Kubernetes says, you went over the limit. I'm deleting you and I'm starting you somewhere else. And this happens again. And if you have a bug, this is going to happen forever and ever until that stops happening. Another thing that we are doing right now is switching to ARM, as many workloads as we can, because we figure out that this is going to save us like 15 to 25% just by switching, just by saying, run this on ARM. If you are running Java, it's very easy. You have a bunch of JDKs that have Docker images that are ARM built. So you can just say, you can do a multi-arc container, Docker container, and then depending on the node, if it's ARM or if it's 86, it's going to download the container that it needs. So it's very easy to be able to switch Java workloads to ARM. And it's a lot cheaper. And it's a lot better for the environment too. Okay, so Java and Kubernetes. Are you ready? Do you have your phones ready? I'm going to do a quiz, and we'll see. There's no winners or losers, because this is a bit tricky. Let me start it. Before we start, it's important that you assume some things, and you'll know why later. Assume that the questions, you're running a Java 11, the latest release, not something from a year ago, not something from 6 months ago, the latest one. Assume you're going to use 4 gigs of memory available in your container, and also assume that you're going to have more than 2 CPUs. And this is important later. So let me get this started. Okay. This running. No, stop. 1 second, sorry. This is not loading. So were you able to join or not? It says let me try a different thing. Present. Okay, so I see some people joined, and for some reason the iframe is not loading, but let me make it. Okay. Maybe I reset it when at some point, by mistake. And you may need to join again if you don't see your name there. Anybody? Not enough coffee? Okay. Sorry? Oh, the QR code is for another poll. Oh, okay, sorry. I thought that, yeah, the number was, because the number was the same, I thought it would be, that's why I don't do demos, but then you screw it up anyway. I'm not even good at opening an HTML page. See? Okay, 21 people. I'm going to have to jump back and forth from one place to another, but that's fine, I guess. Okay, so let's get started. Ready? So what is the default JVM heap size? 75% of the container memory, 75% of the host memory, 25% of the container memory, or 25% of the host memory, or 127 megabytes. And the 127 megabytes, it's a very specific number. Okay. Wow. Assume, as I said, you're going to have more than 2 gigs of memory. I think it was 2 gigs of memory. No, 4 gigs of memory, I think it said. So it's a reasonably sized, assume it's a reasonably sized JVM. It's not one of the new microservices Java applications that you can run in 32 gigs, on 32 megabytes of memory and 0.1 CPUs, okay? Okay, so what is the default heap size? the correct answer is 25% of the container memory. Okay? And somebody got it right. Mitchell got it right. Let me now jump back and forth. Where is my cursor? Here. And the reason is if your container has less than 256 megs of memory assigned, the limit, you're going to get 75% of the container memory. The JVM is going to do the heap size to 75% of the container memory. If you have more than 512, you're going to get 25%. And between 256 and 512, you're going to get 127 megs of memory. So on any recent JDK, which is over one of a few years ago, JDK 8 and JDK 11, Java will detect the memory in the container, not the host. So that was an improvement. Before that, it would look at the host and say, oh, the host has 128 gigs of memory. I'm going to try to use a lot of it and ignore the container limits. So that was an improvement. And it uses a container memory limit. So there's no guarantee that you're going to have that physical memory available. So you got to be careful with what you do. Do not trust JVM ergonomics, because this, as you decide to change or dynamically your containers change the memory limits, you can configure them as you would do in any VM or bare metal machine. You can set the initial run percentage, you can set the max run percentage, and don't set the other one, because this is very confusing name. Because this is to set up something else, the min run percentage one. And you can do this kind of by hand. So what we do is we set the max heap, min and max heap to the same number, and we use 75% of the container memory. And this is typically, I think that's, people agree that this is a reasonable number, unless you are doing a lot of off-heap memory, because you only get 25% of off-heap memory. And things like Elasticsearch or Spark or something like that uses a lot of native or off-heap memory, 25% is not going to be enough for them. What happens is the JVM takes all the memory on the startup, and Kubernetes doesn't see. This is another tricky situation with Kubernetes. Kubernetes sees all that memory as used, because the Java is actually using that memory for the heap. And one advice is set the request and limits to the same value, so you don't get this. You get guaranteed that you have the memory that you requested, and you don't go over that request, because otherwise you would then getting page memory. Okay, so the next question. All right, ready? What is the default JVM garbage collector? Assume more than 2 CPUs. Serial GC, parallel GC, G1 GC, CGC, or Shenandoah GC. So for a big Java application. And what JVM I said? I forgot what JVM. I think it said 11 plus. Okay, almost there. All right. And the right answer is G1 GC, which almost half of you got right. And now we have Mohammed on top. Let's get back. Where is my cursor here? So what happens is you get, if you had less than 2 processors and less than 1,792 megs available of memory, you get the serial. The parallel was Java 8, but we don't care because nobody uses Java 8 anymore, right? Right? And G1 is on Java 11 or higher. what's going to happen, well, obviously you want to tune the garbage collector the right way, but that's not something container or related or Kubernetes. Even if you run on bare metal, you want to do that. And what happens on a Kubernetes world where you may scale up and down your containers depending on different factors, right? Maybe you start with 2 CPUs requests, and then you use autoscalers, and now you either Kubernetes or you tweak the request, or somebody else in a different team or your team tweaks the request. Now suddenly, just changing one value, like the CPU request or limits, changes the garbage collector you're using, and maybe you get different results that you were expecting, and you don't know why. It's because the JVM just switched the garbage collector because you changed a different parameter somewhere else. So again, do not trust the JVM ergonomics, and you can configure the garbage collector explicitly to the one you want, on any case. Serial, parallel, G1, whatever. I put this slide here from Microsoft Azure on the recommendations. There's people that agree with this, there's people that say different things, but it gives you an idea on when it's good to have one or another. Obviously, there's always going to be up to your specific use case, whatever you want to do. All right. So depending on whether you have single core, multi-core, or smaller, larger heaps, or different parameters, and how what is the overhead, and also what version of JDK, because obviously everybody's using JDK 17 now. Now you can use all of them, but if you're not, well, there's some of them that are not available in all the versions. Okay, so again, let's go to the next question. How many CPUs will the JVM be able to use? So same as the Kubernetes container CPU request, same as the Kubernetes CPU limits, or as many as the OS allows. And again, assume a very new build patch version of the JVM. This is a bit complicated, I know, but that's also to show how complicated this getting things right is. So the correct answer today is as many as the OS allows. And it's a very tricky one. Okay, Anders, good job. Let me go back here. So these numbers, same as the container CPU limits, this was on versions before, if I get it right, before October 2022, so around 6 months ago. This changed. Now it's as many as the OS allows, because there was, before that, it was a very weird way of figuring out how many CPUs the JVM thinks they're available. If you say in the container up to 1 CPU, Java will assume there's 1 CPU. If you say from 1 to 2 CPUs, Java assumes there's 1 to 2 CPU limits, I think it was. Now I forgot, but I think it was limits. Java is going to assume there's 2 CPUs, 4 CPUs, and so on. But if you say 1 CPU, if you give the container 1 CPU or 124, which is the same value, the JVM will assume, oh, I can use all the CPUs. So it was a bit weird. And what happened? You can read through the issue on the JDK. They changed this because CPU shares, which is the number that Kubernetes sets. So it was CPU requests. So when you say CPU request in Kubernetes, Kubernetes goes and tells the kernel, the C groups, it says, okay, set CPU shares to this value. And Java was looking at, oh, I look at the CPU shares and see if it's 1, up to 1, I use 1. I think I have access to 1 CPU. If it's 2, it's 2 CPUs. If it's up to 4, 4 CPUs, and so on. But they decided this is wrong. And this was changed in the last patch release in October. Because what happens is this will bite you when you run on a machine with 32 CPUs, 64, 128, a very big machine. Imagine you run on a very big machine and the JVM gets the number of CPUs wrong. Now your thread pools and everything that the JVM sizes based on the number of CPUs that it thinks is available are going to be changed greatly. So you run a tiny container in a machine with 256 CPUs or very big, the JVM is going to make thread pools huge, there's going to make other things very big, but really you don't have that CPU assigned to that container. So again, if you want to be on the safe side, you can also set the active processor count, and you can explicitly tell the JVM how many CPUs you want to recognize. Okay, next question. I think these ones are getting a bit trickier now. In a 32 CPU host with 2 JVMs, and one of them is idle, and both of them have the same CPU requests and limits, 8 CPU requests, 16 CPU limits, how much CPU is going to be used in that node? What is the maximum CPU that is going to be used on that node? So one JVM is doing nothing, the other one is using as much as possible, but both have a 16 CPU limit. I'm giving more time to this question because it's complicated. Okay. And the answer is 16. When you are setting a limits on the CPU side, you are artificially saying, well, not that you're forcing the container to not use more than that number, even if there's CPUs available, CPU time available on the node. You're saying, I don't want you to ever go over 16 CPUs. And the next question that is related to this one, okay. Leaderboard, Asim. Similar situation, 32 CPU host, 2 JVMs, but in this case, none of them have CPU limits. How much CPU is going to be used? So you have 8 CPU requests, no limits. How much CPU is going to be used on that node when at the maximum level? Okay. So we have 8 CPU requests, no limits, both JVMs using as much CPU as they want or they can. And in this case, it's simpler because there's no limits. Both of them, if they are both of them using as much CPU as they can, they're going to use all the CPU of the node. Of course, this is simplifying. I mean, there's going to be other things running on the node, but yes, they're going to be able to use. Congratulations, Asim. You got all of them. Well, 4 out of 5, right? Who is Asim? Yeah? All right. Did you know it, or this was just pure chance? Okay. Let me explain you why this CPU thing works this way, because I think that's the important part. Okay. So CPU requests in Kubernetes are used for scheduling first. When you say, I want 32 CPUs, Kubernetes is going to look and find a node that has 32 CPUs available. And it's going to put your container there, your pod. After that happens, the CPU request is used as a relative weight. So it's not really the number of CPUs that can be used. It's a weight between the different processes running on that node. When you say one CPU, it means that it can consume one CPU cycle for each CPU period. It's not that it has access to one CPU. It has is the amount of time of CPU that they can use. So for instance, if you have two containers only with very small CPU requests, 0.1, if you have two containers with 0.1 CPUs, both of them are going to be able to use 50% of the CPU time of that node. So the request is a weight. It doesn't matter really, it doesn't matter that much once the containers are running. It matters the weight between containers and processes, because at the end of the day, containers are processes. So this translates to cgroups, quota, and period. The period by default is 100 milliseconds on the kernel, and the limit means how many cycles you can use, how many CPU cycles you can use on that time. After you use your CPU time, you are throttled until the next period. I'm going to try to explain it better here. Let's say you have 4 cores, and you have a single thread. You are going to get, and you request you have one CPU limit. You're going to use, with that thread, you're going to use 100 milliseconds of time, the CPU, and when the period ends, you're going to get other 100 milliseconds during 100 milliseconds. So you're going to get the full, you requested one CPU, you get the full CPU every period. But if you say, in Java, it's typical that you're going to have multiple threads. You're going to have the garbage collector. You're going to have multiple things. You're going to have thread pools. So if you have a limit of one CPU or 1,000 micro CPUs, yes, and you have 4 threads, you can consume all the time in a fourth of the cycle. So you have 4 threads, and in 25 milliseconds, you already used your 100 milliseconds of CPU time, and you are throttled for 75 milliseconds until the next period starts. And this is a very tricky thing to find out. I mean, there's metrics. Kubernetes will, I think Kubernetes or your nodes will expose CPU throttling metrics. But the way this is going to show up in your application is very tricky, because it's not like your application is going to be slower. Imagine you are serving request responses and things like that. It's not like, oh, okay, things are very slow. No, it's, okay, things are working for 25 milliseconds, then nothing happens for 75. The next cycle is the same thing. So you get like, okay, something is happening, nothing happens, something happens, nothing happens, and so on. So it's a very tricky situation to get in. You would have to go and look at the metrics of CPU throttling. And this, of course, I know because it happened to us. I didn't know it before, and I never thought I had to go into this detail. But that's very easy to hit this problem when you run Java on containers because of the multi-threaded nature of Java. When you run Node, you don't get this problem because it's all it's not using this multi-thread model. The other interesting things that we use to take Java and move it to this cloud-native world was to use the Kubernetes Autoscaling. It's very easy to use Kubernetes Autoscaling. You get it out of the box. You have 3 models of autoscaling typically. It's the cluster autoscaler, which is the simple one. Okay, my cluster the more things I want to run on the cluster, the more nodes I'm going to get up to the limit. That's obviously very nice, so you don't have to run a max capacity all the time. Then you have the vertical pod autoscaler, which means you are increasing and reducing the resources for each pod based on metrics. Okay, my application is using a lot of memory, give it more memory. My application is using a lot of CPU, give it more CPU, and the other way around. What happens is that right now on Kubernetes, this requires restart of pods. You can make it automatic, and you can make it on the next start. So basically, if you do it automatic, imagine your Java application is using a lot of CPU, and you're saying, okay, tell the VPA to give you more CPU, but that if in automatic mode, it will restart your container. And that's probably not what you want to do. In the next versions of Kubernetes, you're going to have in place autoscaling, so you will not need to restart the container. This will be, for CPU, is not a big deal. For memory, it can be tricky because your heap size is typically calculated when the JVM starts. So what happens when suddenly you get, it's not going to autoscale based on how much heap you are using because the heap is pretty much static, especially if you set max and minimum to the same value. So you will have to change the way your application works and how you configure the heap and so on. We use it only for some environments to scale down for things that are not production. So if there's pods that are not using much memory or much CPU, we scale them down to save money. And we only use it for some specific containers, and the JVM, at the end of the day, the JVM footprint is really hard to reduce. And this saves us like 5 to 15% of resources. The other one is the horizontal pod autoscaler. Is basically creating more replicas when you need to respond to more load. We do it on CPU and HTTP requests per minute. Obviously, you shouldn't be using the same metrics for horizontal and vertical because they're going to conflict. You're going to create bigger pods and more pods at the same time, and the effects are not going to be desirable. There's many ways to do horizontal pod autoscaler. CPU is a bit problematic because sometimes you get the spikes on CPU, and then starting more replicas, it doesn't solve the problem. Let's say you have a periodic task. If you have a bug or if you have something that happens periodically, maybe you start at other replicas, and those replicas start in this using more and more CPU. So you get in a loop, in a cascading effect. So we used also the request per minute, and some other projects use, if you have a queue of things to process, you can use the size of the queue as a metric to create more or less pods. And we use RPM is very suited for us, and as long as you don't have expensive request responses times, that works better. And this saves us like 50 to 75% that if we always run a full capacity with all the number of pods that we needed. And so VPA versus HPA, for a Java application, it's better to increase the memory and increase the CPU. You have a bigger machine, beefier, let's say, a beefier container, and that's going to give you better results than creating many replicas, because all the overhead that you want to have for each replica. But at the other time, you're going to need at least 2 or 3 replicas of your application for HA. So you're going to need minimum 2, probably 3, 1 in each availability zone, and you can configure Kubernetes to do this. So it's going to be a balance between what you want to do. Also, if you have very beefy containers and they're not used, you're wasting more resources. So that was it for me. I think if I have to tell you three things, it's very easy to start on Kubernetes, to lift and shift, especially Java applications, and then you can iterate and optimize. You can use these Kubernetes patterns to decompose the application, so it's better. It runs better on cloud native Kubernetes and so on. We use a lot of sidecars that are easy. We use init containers, and of course, the last step is creating more microservices that interact with your main application. And then there's multiple ways of optimizing the resource consumption that are fairly easy to use, like tuning the JVM, tuning the autoscalers, and so on. You just need to be aware of some gotchas like we were going through, right? So if you have one question, two questions, make me two questions. Just one question. If nobody has any question, don't come later and ask me questions behind the scenes, eh? Okay? All right, well, thank you. You made it.